All right, guys. All right, welcome back. See, 6 of you here. It's a great start. That's more or less the size of my graduate classes, so I just think that's somewhat appropriate. Anyway, yeah, sorry for late start. Kind of feeling under the weather right now. My son has strep throat, and I think I might be picking it up, so we'll see how far I can really get through without my voice giving out. But yeah, so last time we were talking about the spectrum of operators and bounded operators and things like that. We proved a variety of things about them, and I'll review some of that in a minute. But basically, one thing we left unproven was whether or not the spectrum is non-empty for bounded operators. And it is not empty, but we need to prove it. And to do that, we're going to use a little theorem out of complex analysis, and that theorem is Liouville's theorem. And so that it's a really nice theorem about entire functions, which says that every bounded entire function has to be constant. And so with that, we're going to do our best. And let's see. Then after that, I want to start getting into compact operators and ultimately build up to what is the spectral theorem for compact operators. That should be interesting. And yeah, that's the goals for today. Let's see. All right, microphone's working. All right, that's good. And yeah. Okay, so if you have any questions as we go, please let me know. And yeah, it should be fun. I might be leaning a little bit heavily into the textbook today. Some complicated stuff in here that I just don't want to mess up. But yeah, this is a book I lived off of in graduate school. It was the Analysis Now by Gert Pedersen, and this was for my fourth PhD qualifier. I had 4 altogether I had to take. One in basic analysis, one in basic algebra, one in measure theory, and then one in functional analysis. And this is what I lived by for functional analysis. So we'll go ahead and use that. All right, so let's go ahead and jump over to the tablet and happens. Okay, so checking things here. Looks like my microphone is working. If you guys can hear it, last time it just didn't work. I had to like cut a huge chunk out of the stream later when it's on the VOD. But yeah, so I think everything's working right now. Okay, so these are our goals here. So we have the spectrum is non-empty. That's what we're going to prove today. It's going to be the first thing we prove. And then we're going to get into talking about what compact operators are. These are extremely important operators. These are some of the earliest operators that were studied. And basically what we're going to be doing is we're going to try to build up to the idea of the spectral theorem for self-adjoint compact operators. And so we're going to hit, I don't think we've talked about projections yet, so we'll get to that. Talk about what finite rank operators are, and that's important. It's important because in Hilbert spaces, compact operators are exactly those operators that you can approximate with finite rank operators. And essentially what it says is compact operators are those bounded operators for which you can use a top left corner of that matrix and get a good estimation of the operator over the entire space. Let's see. Hey, Effia. So you say, oh boy, I took a course on Hilbert spaces last semester as an undergrad. Yeah. Well, I'll try to be nice here. We'll see how this goes. But this is all operators on Hilbert spaces that we're talking about. And this is, I think it's fun stuff. So, all right. Let's see. Okay, so I think I have everything I need here. Let's start talking about the spectrum and non-emptiness of the spectrum. So let's see, if I have talked about the last week here, we defined a bunch of stuff about the spectrum of an operator. And so definition of spectrum, Yeah, okay. So here, last time we had the definition of a spectrum for a bounded operator. So essentially what we said is that it is a collection of points lambda in C such that A minus lambda I is not invertible. And so there's really simple examples. If M is a matrix, then if you have lambda as an eigenvalue for that matrix, then that eigenvalues are inside of your spectrum. So here we have that M minus lambda I. If V is in the spectrum, then that is going to be sent. If V is an eigenvector with eigenvalue lambda, then it is sent to 0 by this, which means that the null space of this operator is not just simply 0. And so the rank nullity theorem tells us that it is also rank deficient. And so that means that it is not surjective, and it is also not injective. And so therefore, lambda, that should not have been written that way. It should be written is inside of sigma of M. And so, so that's it. So our easiest examples of where this happens, where this operator is not invertible, are matrices, and in general, any operator with an eigenvalue is not going to, or if this is an eigenvalue here, then this is not going to be invertible. So that's tells us what our spectrum is, but I didn't tell you whether or not it was bounded. We did have a couple of results in here, though. We saw that if where'd it go? Yeah, there we go. So we showed that if lambda is bigger than A, then lambda is bigger than the norm of our operator, then we have that lambda is not actually in the spectrum, it's in what we call the resolvent, or the complement of the spectrum. And so that tells us that the resolvent for any bounded operator is non-empty, but it doesn't tell us anything about the spectrum. But another thing we did get out of this, though, is that the resolvent itself, the resolvent set, is an open set in the complex numbers, which gave us that the spectrum, being its complement, is closed. And we also see that it is bounded because for sufficiently large lambda, they're going to be in the resolvent and not in the spectrum. So then, therefore, it is a bounded compact set inside of the complex numbers. Complex numbers have the Euclidean topology, which means that it is a compact set. So that's pretty nice. So, so then we'd like to say that it's not only a compact set, but it's a non-empty compact set. And so let's go ahead and start with that. So, theorem for a bounded operator A inside of L of H. That's our set of bounded operators, where H is a Hilbert space. Then for a bounded operator, we have that sigma of A is a non-empty compact subset of complex numbers. All right, and so that's what we're going to be trying to prove. All right, so let's see, NIAS 2631. Wow, I wish I had known this was happening, stuck in the office. Oh, I'm sorry. Yeah, I need to be better about scheduling this. It's hard for me to figure out exactly what time I'm going to put this up, because sometimes I have to spend a lot of time reviewing beforehand, and I only get like a small window from when I like basically drop my kids off on Wednesday and able to actually do this. But generally speaking, I'm trying to aim to have this from sometime around 11 to 11:30 is when I'm trying to to launch it, and then it runs for about an hour. It will be released as a VOD later on, so video on demand. So if you go to my channel later, you can catch any of this that you want. So you don't have to be here at the moment, though it is very nice to have those of you who are actually here watching right now, because it actually gives me somebody to talk to. So, all right. So now, so we're trying to show for this bounded operator A, and that is a bounded operator over our Hilbert space, that sigma A is non-empty. We already have its compact set, so we'll just write that down. So proof sigma of A is compact from last time. Okay, so now let's show that it is in fact non-empty. All right, so we're going to assume by way of contradiction that sigma of A is empty, so that there's no elements of the complex plane that are inside of our spectrum. So I then consider A minus lambda, or I'll say lambda minus A, just -1 times this, for norm of lambda bigger than norm of A. Then, and I'm going to set this operator, this function, capital F gamma, let's just say for little f and g inside of H, we're going to define this. It's the sum of, or I should say, let's see. So it's going to be lambda minus A acting on F inner product with G. And we're going to have this as the inverse here. So we know that that is invertible from last time if the norm of this complex number is bigger than the norm of A. And so so we can define, so we know this inverse is well defined. And I'm turning this into a function that's going to take us from lambda to the complex numbers, because the inner product lands back in the complex numbers. F and G are arbitrary. And so essentially what I'm going to be trying to show to achieve this contradiction is that lambda minus A inverse has to be the 0 operator, which is not really possible because 0 isn't the inverse for any operator. And or conversely, you can basically, well, yeah, I mean that's the best way I can say it. And so what we're going to show is that f lambda, capital F lambda, is going to be the 0 function for every choice of f and g. And since g can be chosen arbitrarily, that means that this first component would then have to be 0. And so then that means that the operation of this guy on any f has to be 0, which then makes this guy the 0 operator. Okay, so let's go ahead and work this out. All right, so what we can do is we can use the series representation that we established last time. What I'm going to do is I'm going to factor out this lambda out of here, and so that's going to come out as I think it's lambda here. We might have to make some adjustments later, but we'll see how this works out. There you go. Sorry, I did this on my whiteboard a minute ago. Yeah, okay. So yeah, this is going to come out as lambda inverse, and it's going to leave us with I minus lambda inverse A, F, G, like that. And so then what we can do is we can go ahead and we get this. So it's going to be lambda inverse, and in the inside here we get the sum of lambda to the minus n times a to the n acting on f g. And then we can go ahead and exploit the continuity properties for convergence and sums and Hilbert spaces and the inner product. And so we end up getting this. It's the sum of lambda to the minus n of inner product of an, f, and g. Okay, so what we can see here is that this is actually sort of a power series in lambda minus 1, and this is an analytic function. So what we can do is we can go ahead and, well, first of all, we can demonstrate that this actually converges, right? And that's actually not too hard. What we get is, if we take a look at f lambda, then this is going to be less than or equal to the sum, well, let's see, we're going to have 1 over absolute value of lambda times the sum of 1 over absolute value of lambda to the n, and we can use the collection of Cauchy-Schwarz inequality. We can use the Cauchy-Schwarz inequality and also the Banach algebra inequality that we get for the operators, and we get this. And so, this converges just fine, provided that lambda in magnitude is bigger than the norm of A. And so, and in fact, what we get is that this is equal to the norm of f times the norm of g divided by absolute value of lambda, and then we have 1 over 1 minus norm of A times lambda inverse. And simplifying this a little bit, this is going to end up giving us norm of f times the norm of g times 1 over norm of lambda minus norm of A. And so we see then that f minus the norm, or the magnitude of f lambda as a function taking the complex numbers to the complex numbers, this guy tends to 0 as the magnitude of lambda goes to infinity. Okay. So outside of so thus far this is pretty straightforward. It's a triangle inequality. We did exploit one thing here, where basically this guy, we have the norm of an is less than or equal to a to the n, and and a couple other things, but it wasn't too bad. But we see that this function is going to 0 in magnitude as we go off, as lambda goes off to infinity. And so that would be fine for maybe an ordinary function, but this is going to turn out to be an entire function. And if that happens with an entire function, then that means that the function has to be identically 0 for all lambda. So, so now what do we need to do? Well, we need to show that it's actually an entire function in order to complete our proof. This is a perfectly fine analytic function in our sort of like reciprocal variable, 1 over lambda. And the radius of convergence here is going to match with the distance to our first sort of singular point. And so the radius of convergence for the series representation of f of lambda is the distance to the first singular point from the origin. But since we're always going to be analytic, we're always going to be invertible, but since sigma of A is the empty set, there are no singular points. Hence, f lambda is entire. So, which implies by Liouville's theorem that f of lambda is equivalently the zero function, which implies that lambda minus a inverse acting on f is equal to 0 for all f in H, which implies that lambda minus a inverse is equal to 0 operator, which is a contradiction because 0 operator is not an inverse for any bounded operator. So that means that there has to always be at least some element of the spectrum, which is pretty nice. Okay. So, let's see. One thing that might be interesting just to mention is this. We can ask the question, what sets are allowed to be the spectrum of an operator, of an operator. All right, so that's the question. All right, well, what we know is that spectrum has to be compact. So we know at the very least it has to be a compact set. Turns out any compact set could work out. And so what we can do then is we're gonna let, say, K be a compact subset of the complex plane. This double subset often means compact. And we're going to pick a sequence in K, let's call it xn, such that xn closure is equal to K. We know that K is separable because complex planes are separable, which means you have a countable dense subset. So this is possible to do. And so what we can do then is we can actually cook up an operator that is where every xn is actually an eigenvalue for that operator. So then we're going to let, say, E sub n be an orthonormal basis for H, a Hilbert space, and set the operator T, which will act on, say, a function f as the sum of xn against f en n going from 0 to infinity. And so if I have T on en, then that's just going to give me xn en. And so then, therefore, xn is inside of sigma of T, because they're all eigenvalues. And that implies that sigma of T is equal to K, because is that going to imply that it's equal to K? certainly that K is a subset of that, right? Yeah, I think that should be sufficient. No, we can talk about it later. I didn't really think this example through. But yeah, but that definitely does give you the entire thing there. Just trying to think if there's any gaps. So what's interesting here, though, is that if K isn't actually a countable set, then that does mean that that this T, even though it's spelled out in terms of eigenvalues, it will actually have some of its spectrum that aren't actually point spectra, because any element of K can actually be approximated by these xn's. And so, and which means that we have the complete list of eigenvalues here, so nothing else can be an eigenvalue, but we know the rest of K is actually still inside the spectrum because the spectrum is compact. And so that gives us access to other kinds of spectra in this example too. Okay, so now we want to get to, let's say the road to compactness. All right, so we have shown some things about the spectrum for general operators, bounded operators, and I want to talk about the spectrum of compact operators. And so in order to do this, we're going to have to learn about what compact operators are, and then over the next couple lectures, we're going to prove a bunch of little things about them until we can get to a full description of the spectrum of compact normal operators. And so they're pretty cool objects, and essentially one thing you should know about them is that they're basically limits of matrices. So for any bounded operator, you can always cook up some sort of matrix. So A00, A01, A02, etc. A10, A20, etc. A11, etc. So you can always do this for, you can make up a matrix representation for a bounded operator. However, if you take a look at a segment of this, that doesn't always lead to a good approximation of the bounded operator. And one operator where this is significant is that if we take a look at just the identity operator, any upper corner of the identity operator, a sequence of upper corners of these identity operators won't actually lead to convergence in the operator topology, and that's problematic. It will lead to convergence in the strong operator topology, but often if you want to talk about things like spectra and things like that, you want to be talking about the norm topology. You want to be talking about norm convergence, because as we saw before, if we have two operators that are close together, then their spectra is going to be close together. I think I proved that last time, maybe. And so so compact operators are nice because they admit norm convergence when you make this upper left corner larger and larger. And so you can say that you are confidently uniformly close, in a sense, to the operator that way. But you can't say the same thing if it's something like the identity operator or just an arbitrary bounded operator. So another way to characterize this upper left-hand corner sort of idea is that we need to talk about finite rank operators. So this, if you just take this segment of this operator, it looks like it should just be a 2x2 matrix, and so and so then if you hit it against something, then what's going to pop out is a two-dimensional vector. Now, I mean, it's a little bit more complicated than that, but it's not that much more complicated. And so essentially what we're going to be talking about are operators whose range have finite dimension or have finite rank. And so we're going to define that. So finite rank operators. So so definition. If A is inside of L of H, and the dimension of the range of A is finite, then what we say is that then A is called a finite rank operator. Right. And so projections serve as a really good example of finite rank operators. In fact, they can be used to turn basically anything into a finite rank operator. One property of finite rank operators in particular is that they serve as an ideal. And so we say, so proposition, it's a really easy thing to prove. Proposition, if A is finite rank, and B is inside of L of H, then AB and BA are both finite rank. And so, in other words, if LF is the set of finite rank operators, then it is an ideal. Okay, so so proof. Let's go ahead and do that. Should prove something eventually. So the proof here is fairly straightforward. So we're assuming that A is a finite rank operator and B is inside of L of H. We should note that the range of AB is actually just a subset of the range of A. So dimension of the range of AB itself is finite. Right, so that one's trivial. The other one, let's see how we do that. So basically what's getting inputted into B is going to be a finite rank. So it's a finite dimensional vector space. And then B is going to be a bounded operator acting on a finite dimensional vector space. But yeah, okay, so let's do this. So let's go ahead and say let the set V1 up to Vn be a basis for range of A. Then we have this. AF is going to be written as, say, alpha 1 V1 up to alpha n Vn. And for any, we're going to let F be an H. And then we have this, and BAF is going to be equal to A1 BV1 up to alpha n BVN. And so the range of BA is equal to span of BV1 up to BVN. And so it's finite dimensional. And so out of space, but I'll put a block here. It's finite dimensional. So that's how you get that. Obviously, the alpha 1s through alpha n's depend on the choice, depend on f. But once they're determined through AF, they're going to be determined through BAF. And so our new basis then becomes BV1 up to BVN. Well, I shouldn't say that is a basis, because the application of B might actually cause this to have a smaller dimension. So I know I know the range of BA is in the span of these BV1s through BVNs, but we might not actually need all of them. But that's not really a problem we care about. We just want to show the range is finite dimensional. Okay, so that's nice. All right, so those are finite rank operators. Finite rank operators form an ideal, which is nice. I can give you an example of a finite rank operator. And so an example of a finite rank operator is this. So we're going to say, suppose that V is a finite dimensional subspace of H. And so it's a finite dimensional subspace of H. Then something we know from Hilbert space theory. Then V is a closed subspace. And thus, let's see, is a Hilbert space as well. So what we can do is we can I can either invoke projections if you already know what they are, but if you don't know what they are, we can just sort of manufacture a projection. And so we can it is a closed subspace, so that makes V a Hilbert space in its own right with the same inner product, and there exists an orthonormal basis, say E1 up through En, and orthonormal basis. And so then we define P sub V acting on F as the sum of F against En times En, and equals 1. Oh, I put, let's make it capital N. N equals 1 to capital N. And so this is an operator. This is a projection operator. And let's see. A controllability matrix would be also a finite dimensional operator. Yes, I believe so. It's been a minute since I've looked at controllability matrices. I usually work with nonlinear controls, but yeah, I think it works. Let's see. Okay, so then here we go. We have this projection, and P of V is P of V. The range of P of V is actually all of V, because it leaves V alone. P of V acting on an element, say F equals F for F in V. And then something else we know is that if F is inside of V perp, then we have that P of V acting on F is equal to 0, because we're basically going to be taking a look at the inner products of F with all these different elements of V. And so if F is perpendicular to everything in V, that is perpendicular to all these guys. All of these become 0, and so PV of F equals 0. All right. Yep. So there we go. Yeah, and so on the controllability matrix being finite dimensional, a finite dimensional operator. Well, it's a finite rank operator is really what we should say, and the dimensionality of the range there is going to be just Rn usually, right? And so I mean, yeah, that would fall under the example there. Just trying to remember how we would put that together. I don't know. Yeah, we can put that on the list of things to cover in this series. I'm actually going to teach a graduate course in mathematical operator theory next spring, and so I probably should get rehearse all these little proofs and things from control theory. So I'll probably be doing that. And what better place than the stream where the world can judge me and seeing how badly I remember things. Okay, so yeah, let's see. Yeah, no pressure. Okay, so here we are. So we're on our way to compactness. We have finite rank operators, and that's great. Let's go ahead and let me double check what I wanted to talk about. So on the list here, I have I need to talk about projection operators. We just defined what one projection operator is, but we can do better. I need to talk about what diagonalizable means. All right, and so that's something that's going to be important in a second. And we did define finite rank operators, so that's good. And then after that, we have our equivalence of compact operators. Oh yeah, I mean, I'm not saying you guys are judging. I'm just saying, like, it's a little nerve-wracking to come up here and try to do all this stuff. I'm trying to be on top of things, but you know, it's I present myself as an expert, but you know, even experts forget things. Let's see. Okay. What's next? All right, so projections. I like that. Not remembering is not a crime. Not having passion is. Yeah, maybe that. Maybe we should make a T-shirt for that. All right, let's see. Okay, so projections. So let's talk about definition. All right, so we're going to be talking about projections. So given a closed subspace of a Hilbert space, let's say capital V, there exists an operator P on V on H such that what we get one, I guess P acting on a little V gives us a little V for a little V inside of V. 2, P of W is equal to 0 for W inside of V perp. 3, P squared is equal to P, idempotent. And 4, P star is actually equal to P. To be honest, all you really need is 3 and 4, and you can get 1 and 2 through a bunch of other theorems and things like that. But we're just going to put this as part of the definition here so we don't have to worry. And so, yeah. Stole it from Beethoven. To play a wrong note is insignificant. To play without passion is inexcusable. Oh, that's good. I like that. Yeah. All right. Let's see. All right. So that's a projection. So we have an example of a projection here already. And so projections you can always make this way. So if you take some closed subspace, that a closed subspace of a Hilbert space is itself a Hilbert space, so it has an orthonormal basis, and you can cook up the projection this way. Always works. what we use in this example is that it turns out that every finite dimensional subspace of H is automatically a closed subspace. So, so we had a lot of this come in for free. So from here down really applies to all Hilbert spaces, all closed subspaces, and then we just get this guy is a closed subspace. Okay, so great. Let's see. So that's what projections are, and we will need them. Okay, now let's talk about what it means to be diagonalizable. So diagonalizability, I mean, if you learned in linear algebra, basically means that you are similar to a diagonal matrix. And if you can have and we say that an operator that is diagonalizable, basically if it has if its collection of eigenspaces spans the entire vector space. Now, that's kind of what we want to happen here as well. And so what we're going to do is we're going to take, we say an operator T, an operator T, which maps from H to H, is diagonalizable if there exists a bounded subset, I guess. Say lambda n subset of C. There exists a bounded subset lambda n of C, and an orthonormal basis of H, say En, for which we can express T as this. So Tf is equal to sigma lambda n f against En, n equals 0 to infinity. All right, so this would give us each of these Ens are an eigenvector for T, and lambda n is an eigenvalue. So this is exactly what I wrote earlier, and so this is a diagonalizable operator. And so what we want to do then is, what was I going to do? Hold on. Right. So we have a special sort of idea for what we call this operation. This is called a rank 1 tensor on F. So we often write this as En against F. And so another way to write this is this. So En cross En acting on F. And so in other words, if there is an orthonormal basis for which you can write Tf as a sum of rank 1 tensors here, or a series of rank 1 tensors, then we say that T is diagonalizable. And what's significant about the rank 1 tensors is that, so this is where we have the left and right of the tensor actually matching. But if I change one of these guys to another member of a different orthonormal basis, then this is exactly the singular value decomposition. And so we have, or singular value expansion, which is nice. Okay. Okay, so I wasn't here at the start. Was there any assumptions for the theorems regarding positive definiteness, positive semi-definite? No. So far, we haven't said anything about positive definiteness of these operators. The only thing we're really assuming about the operators at this point is just that they're bounded. And so, but we later on, we'll probably need to talk about some positive definiteness and things like that, but probably not this lecture. But what we can get is whether or not these operators are positive definite, just by looking at sort of their lowest a diagonalizable operator we can say is going to be positive definite if all the lambdas are positive and strictly bounded away from 0. And then that would get you something about positive definiteness. Okay. But yeah, when we talk about reproducible kernel Hilbert spaces in more detail, we'll be talking a lot about positive definite matrices, positive semi-definite matrices, and positive definite functions. And I use Holger Wendland's book a lot for that, scattered data approximation. And I taught a course on that at my own university last year, I think. I really wish I could just share a lot of my actual lecture videos on YouTube, but there's the FERPA laws keep me from doing that, because no student should be identifiable, and so yeah. Okay, let's see. So we have that. Good. All right. Just going through a list of things I want to talk about. I only have about 10 minutes left, and so I'm going to go ahead and just lay out compact operators, one definition for them, and then I'm going to spell out a whole bunch of different equivalent definitions. And I don't think I have time to go through and prove all of them, but we'll see if I can take a shot at one or two. My kids have early release day, so I have to duck out a little earlier than what I usually like to. All right, so let's talk about definitions. So yeah, at this point, we're just really trying to build up an infrastructure for us to actually start proving things on top of. And so for this, we need definitions. It's like, I really wanted to just dive into everything and just talk about spectral theory for compact operators, but then you start looking at the theorems and you're like, oh wait, no, I need to define this. Oh wait, no, I can't do this until I define this other thing. Nope, gotta define this other thing. And so it becomes a sort of laundry list of things that we have to cover as definitions before we can actually jump into things. Unfortunately, I won't be able to get all the way into these compact operators, but there's one really basic definition. This is one I more or less live by when I'm working with compact operators, and mostly because I just work with them over Hilbert spaces. So an operator T, or well, let's just say A, mapping H to H over a Hilbert space H is compact if there exists a sequence of ANs inside of LF of H such that the norm of A minus AN converges to 0 as n goes to infinity. And so if we define, let's see, we have a nice symbol for compactness. I'm just looking at this book. It depends on the book you look at. Sometimes it's defined as like, I don't know. Well, for us, we're just going to say we'll call L0 of H the collection of compact operators of and so essentially what we have is we have LF of H is a subset of L0 of H, which is a subset of L of H. I should probably use an operator, bounded operator. And what we're saying is that L0 of H is equal to LF of H closure under the norm topology. So put like of that. Okay, so we have these compact operators, and I usually like to think of them as just sort of growing matrices, or so basically you take finite rank operators and just like let them fill out the space until you get a compact operator. Now every finite rank operator is automatically compact, but we're taking the closure of these. So we could have these compact operators that are, so we can have these compact operators that have a non-finite rank. And so one example of this sort of thing would be if we take t of f, let's just cook up something, we have 1 over n f en en. And so this would give us a compact operator, and basically we see that it has eigenvalues of 1 over n, and those eigenvalues are tending to 0. And so what we're going to get if we take a look at spectral theorem for self-adjoint compact operators, let's say example is compact. And so what we can do is we can take a look at the spectral theorem for compact self-adjoint operators, and what we're going to see is that its spectrum is a sequence of points, and that sequence of points goes to 0. So if you have a sequence that doesn't tend to 0, then it won't correspond to a compact operator. Okay. So we have, so let's go ahead and conclude and set up for next time. I do apologize that this was sort of maybe a little foreshortened. But let's set up for next time. The following are equivalent. All right, so 1, we have that T is compact, or I should say the operator T is inside of L of 0 of H. 2, T is weak norm continuous. 3, what was another one? T of B is compact, where B is the closed unit ball of H. 4, T B closure is compact in H. And 5, this is one that's going to take a bit. Each net in B has a subnet whose image under B under T converges in H. And so this is Gert Pedersen that I'm pulling this from. But a lot of this is actually fairly straightforward. So 2 things that are actually going to require proof is going to be 1 to 2. It doesn't take much of a proof, but basically getting that you're from a finite, you're a limit of finite rank operators to T being weak norm continuous isn't too bad. Now getting from T being weak norm continuous to this guy being compact, this just uses an idea out of Hilbert space theory, which basically, Banach space theory. So Alaglu's theorem tells you that the closed unit ball in a Banach space is going to be weak star compact. But for a Hilbert space, weak star and weak topologies are the same, so that means that it is weakly compact. T being a weak norm continuous operator means that we have it's taking us, it's continuous and with the weak topology in its domain, and we know continuous functions take compact sets to compact sets. So that gives us immediately that TB is compact. Well, if TB is compact, then the closure of TB is compact, but that's trivial. TB was closed in the first place, so the closure doesn't do anything. And then to get to 5, basically the subnets, you can think of them a lot like subsequences, and we can talk about what nets are next time, and that might actually be a great way to open the next one. But basically, general topologies aren't completely described by subsequences, by sequences and subsequences like metric spaces are. So you need something else to fill in there, and because analysts really love our subsequences, we went ahead and just invented nets, so we don't really have to think about topologies anymore. So nets basically behave mostly like sequences with a few caveats. And so it turns out that if you have a compact set, then basically every net inside of a compact set has a convergent subnet. And so then 4 gives 5 immediately. So the things that we're going to talk about next time is that we're going to really need to show that 5 proves 1, and then we're going to need to show that 1 proves 2, and then the rest just follow immediately. And so the next time, in order to really understand what's going on, because I know some of you guys probably have never seen nets before, we're going to have, I'll tell you guys of what a net is, and then we'll talk a little bit about weak topologies, so we can get through this without too much trouble. Okay, but at this point, I need to go get to the car and drive across town to pick up my kids. So I appreciate you guys coming in here, sort of unexpectedly, me just like chiming in, me just opening up and giving a lecture. And but yeah, next Wednesday, I'll try to give another one, and we'll pick up from where we left off here. And then the week after that, I don't think I'll be here, but then the week after that, I probably will. Anyway, but I'll keep in touch, and I'll try, now that I've actually been doing this more consistently, I'll actually put it on a schedule so that you guys will know when it's coming up. Anyways, thank you all for coming, thank you for watching, and I hope you all have a great day.